Hello, everyone. Thank you for joining us on a new session of the TVS Science Colloquia. Today we have the pleasure of having Maria Pruzhinskaya with us. She's postdoc at Clermont-Ferrand working on anomaly detection. So please, Maria, take it away.
Hello, everyone. Thanks, Priscilla, for presenting me. Yeah, I just add that Clermont-Ferrand is in France. And I'm glad to talk today about SNAD. SNAD is a project devoted to the anomaly detection problem in astronomical databases and catalogs. By the way, so if you have some questions, please feel free to interrupt me, and maybe something will not be clear, so I will clarify. But first of all, SNAD is people. We are international collaboration. We have researchers from different countries, mainly from France, Russia, United States, and United Kingdom. And every year we organize the so-called SNAD workshops, also in different places in the world, where we working on some interesting astrophysical problems related to big data, anomaly detection, and machine learning. Here I just share some group photos from different meetings. So I'd like to start with a definition of anomaly. What do we mean by anomaly? Roughly speaking, we could say that there is a machine definition of anomaly and human definition of anomaly. Machine definition of anomaly is rather simple, so it's a statistical definition. Let's say that you have some data and you describe your data with two parameters, X and Y. And then you look at the distribution of your data in this parameter space. Those objects that are normal will be clustered as it is presented here in some regions N1 and N2. And those that are located separately, it could be a small group of objects, small cluster, or it could be some individual objects, will be an outlier from the point of view of your algorithm. But it is important to stress here that this definition is not necessarily correspond to the human definition, because by anomaly, we usually thinking about something new or about something interesting or rare, because the outliers that objects that considered by outliers by your algorithm not necessarily astrophysically interesting, because, for example, there could be some artifacts on your light curve if you are talking about photometry. So imagine some supernova light curve, and there could be few points that just have a wrong photometry. So from the point of view of the algorithm, the light curves would look weird. So it could point it as an outlier. From the point of view of human expert, it will be rather clear that, okay, this is a normal, I don't know, type 1a supernova, and these 2 points or 3 points are just some problems with the photometry. Also, as outliers, algorithm could point some artifacts on CCD, on your data process, and this is again not the astrophysical object. Human definition, so really more difficult and depends on your task, because what is an outlier or anomaly for me, not necessarily an anomaly for another person. For example, for me as an expert in supernova stars, I would search for some rare supernova, for peculiar supernova. For a person who is an expert in cataclysmic variables, this probably will not be very interesting, but some unusual cataclysmic variables will be. So this really depends on your domain, but also depends on your task, because imagine that you are working with a catalog of some particular class of object, for example, catalog of quasars. You don't expect to see some other object in that catalogs, but you could run the anomaly detection algorithm to search for cases of misclassification. So the cases of misclassification, I don't know, could be some superluminous supernova, so some contaminants. Maybe the object itself will not be very unusual, but could be anomaly in the sense that we are searching some misclassification in a catalog of particular objects. In SNAD, as anomaly, we consider everything that is rare at this moment of time. For example, kilanovae we consider as anomalies, but maybe in 10 years when we will have hundreds of them, we would not consider them anomalies anymore. So any rare kind of objects, and also we are searching for something completely new, something that represent the new physics. On this slide, I show like the main steps of our pipelines. We are mainly working with light curves, so with photometry. And as you all know, astronomical light curves are quite complicated. So sometimes, so they are not homogeneous in time. We have errors. Well, we have redshift. We have a lot of factors that makes them difficult, and especially difficult for machine learning algorithm. That's why before running any algorithm, we need to pre-process somehow our data. So we need to extract some features. These features could be photometry. These features could be something like amplitude, mean, standard deviation, etc. But after this feature extraction, so it's all go to a different machine learning algorithm developed for anomaly detection specifically. After that, we have a list of objects that are ordered by the anomaly score. And what is important here is that machine learning produces recommendations only. So this is not the point where we should stop, because as I said, machine learning definition of anomaly is different from a human definition. So the objects that we get here would be not interesting astrophysically. That's why we need the next step. We need the experts who will look at this list. Of course, it's impossible to scrutinize them all, otherwise why we would need machine learning, but experts could scrutinize, let's say, the reasonable amount of the candidates, of course, using some additional information like cross-match with different catalogs, images, simulation, follow-up, well, whatever is known for each particular object, and make a decision if it is not interesting, or very interesting. In case we find some very interesting objects, we usually try to get more additional follow-up observations and write a publication in the end. What is important here, also, you could see this arrow and saying active anomaly detection loop. This is a kind of philosophy also that we apply in SNAD. We can call it active anomaly detection. We developed the so-called coniferous package. It consists of 3 different algorithms. The first one is our implementation of scikit-learn isolation forest, and there are 2 other algorithms: active anomaly detection algorithm, active anomaly discovery, and pine forest. So those 2 assumes that there is an interaction between the machine and human. So human could provide its expertise, its opinion about each object back to the algorithm, and at each step of the pipeline. So algorithm could learn from the expert what kind of objects are interested and what kind of objects are not interested. How it works. So both active anomaly discovery and pine forest start with a simple isolation forest. In each node, we take some feature, could be an amplitude, and some separation for this feature. And then all the objects that have a value greater than something goes one side, lower than something goes another side. And in the next node, the same. We take some random feature, take some random separation, and again, objects that have values greater than something goes this side, lower than something goes another side. And many times like that until each object will be separated in a leaf. So after that, so this is called a tree. After that, we could make build another tree and another and another. And then for each particular object, we calculate the distance between the root node and this object, kind of an average distance. So the idea behind is that the most anomalous object will be separated in a leaf first. So after the run of that algorithm, we would have a list. So all our objects will be ordered by the so-called anomaly score, which basically means how fast they were separated in average in a separate leaf. So the active anomaly part happen when you take the first object, so the object with the highest anomaly score, and show it to the expert. Then expert look at the object, again using everything that is available, and if the object is interesting, it gives back to the algorithm the answer, yes, the object is interesting, so nothing will happen. So it means that algorithm works pretty well, and the second object from this ordered list will be shown. Till the moment the object will not be interesting for the expert. And then the expert provides the answer no. And depending on the algorithm, because as I said, we have two different active anomaly detection. So it will be either kind of reweighting of those leaves where there is that not interesting object, or it will be just filtering out of the trees in pine forest. And so by several, let's say, iteration like that between expert and the algorithm, algorithm is supposed to learn what kind of objects are interesting for the expert. Below on this slide, I show two plots. They are the same. Just one is for simulating data, for simulations, and another one is on real data. This is fraction of anomalies depending on number of candidates scrutinized by the expert. In blue, it's a random sampling. So we randomly say to each object, yes, it's anomaly, no, it's not anomaly. Then in orange, it's isolation forest. And green one is our active anomaly detection algorithm. So you could see that fraction of anomalies for the active algorithm is much bigger than for the standard isolation forest. So it means that this active loop works rather effective. Now I'd like to share some of our results, also using this active anomaly detection approach, but this one a little bit later. So first results I'd like to share. It's actually our first work. So our first attempt to search for anomalies using light curves from the Open Supernova catalog. So it was a really kind of a first try. So we extracted the light curves. Well, as you probably know, Open Supernova catalog is not supported anymore. So this is quite an old work. So it was in 2019. So we extracted the light curves in different features from the catalog. And then we approximate them with the vector Gaussian process. It's actually probably one of the most important outcome of this work, the development of this vector Gaussian process, because if you ever try to approximate any transient, any light curves, not of a very good quality, you know that it's a kind of a tricky task. And this vector Gaussian process takes into account the correlation between light curves in different pass bands. Let's say if, for example, in G band, you have a good coverage, good photometry, a lot of points, I don't know, like a point every 2 days, every 1 day. And in another band for the same transient, you have a huge gap. Then this approximation works the way that it would look at the shape of the light curves in a band where you have more photometrical point and kind of mimic its behavior. There is no physics inside. It's a pure math, but for some tasks, it's still quite useful. So we use this vector Gaussian process to approximate our light curves, and we extracted a lot of features which are basically just photometry with a bin of 1 day and some parameters of approximation. Then we implemented some dimensionality reduction to the data and used simple isolation forest to search for anomalies. So as a result, we found several superluminous supernovae and several peculiar type 1a and core collapse supernovae. Well, they were all known and all spectroscopically classified. This was a kind of a proof that this approach works. And also an interesting output was that we found several cases of misclassification in the Open Supernova catalog. So that's supposed to have only supernova, right? So we found, for example, this binary microlensing event and several AGNs. So now we are working with the light curves from the Zwicky transient facility. Not the alerts, but we are working with catalogs of the Zwicky transient facility, so the so-called data releases. And here, so we are actively implementing active anomaly detection algorithms that I mentioned a few minutes ago, and also trying to use them as a targeted search. As I said, using this active approach, you can teach your algorithm to search for the object of your interest. It means that I could, for example, say to each supernova like candidates that this is anomaly, and to everything, to all other kind of objects that this is not anomaly. So like that, I could teach the algorithm to search for supernovae. And so this we actually tried a few years ago. So we ran our algorithm on 27 million light curve from ZTF to search for supernova candidates. And we found more than 100, there is a kind of update, 150 supernova with this approach. And what is interesting that some of them were not yet published. well, basically, yes. So these 144 were not yet published. So we posted them to TNS. And what is interesting is that some of them were actually missing in official alert stream, despite having very well sampled early light curves. So I show a few examples here. So you could see that there are some classical 2P or collapse supernovae, some very nice type 1A supernovae, even with a very nice rising part. So we could not, of course, since the data were found, the supernova were found in data releases, we cannot go back and get the spectra, so we could only classify them photometrically. So we tried to model them with a few simple models to identify some type and redshift, yes, if needed. But what is important is that we should not miss this kind of discoveries, this kind of transients, maybe when we plan future missions or for SST, because as I said, some of them have really very nice light curves, but for some reason were not in alert stream. Also among those supernovae, we found several very nice candidates to superluminous supernovae. So there were 4 candidates that we found. You could see there, I think, yeah, it's R-band light curve here in comparison with the known superluminous supernovae 2006 JY. Again, we could not go back and get the spectra. And for example, since we discovered them, there were some more observations of this region made by ZTF. And this green one looks like to be active galactic nuclear, because sometime later, we saw that it has a rebrightening, and the light curve really looks more like AGN than superluminous supernova. But some candidates still very promising superluminous supernova candidates, especially this SNAD 160. For which we actually obtained additional follow-up observations. So not of the supernova itself, but of the host with Keck telescope, and determines its redshift, and also try to model it with the stellar code. It's well, for a moment, it's just preliminary modeling. So the progenitor, the best parameters for the progenitor assume the mass of pre-supernova about 250 solar mass, which makes it to be a very good candidate to peri-instability supernova, theoretical class of supernova that were not yet observed. So apart of doing some targeted search with active anomaly detection, we of course just do some anomaly detection in general, and among the outliers that we get from the algorithm, we have a lot of non-cataloged objects like active galactic nuclear, well, candidates in active galactic nuclear, candidates in quasars, this nice candidate in a luminous blue variable that potentially can explode as a supernova. Some of the objects we follow up spectroscopically and photometrically. For example, here you could see a folded light curve of a variable star. So we could not classify it using just photometry. So we got some additional spectral observations with 2.5 meter telescope and established its type as RS Canum Venaticorum variable. So it's a binary system with a chromospheric activity. So the stars have a very big spots. So, and this is probably what we see as a variability. Also, among the candidates in anomalies, we found a lot of M-dwarf flares. I will talk about them a little bit later. Some microlensing candidate as this one. So you could see that it's really symmetric and there is some feature here. So probably binary microlensing event of some planet. Some optical counterparts of radio sources, and a lot of uncatalogued cataclysmic variables. One of such findings, actually, some M-dwarf flares makes us thinking about initiating a separate sub-project devoted to M-dwarf flare search in ZTF data. So we took around 35 million ZTF light curves and implemented two different approaches. One is a standard approach, so the parametric fit. And another approach is a machine learning algorithm. So we again use active anomaly detection algorithm as a targeted search. So to look for more objects like that in ZTF data. And so we found 134 flares. This is the biggest sample of ZTF flares, as far as I know, for this moment. And for 13 of them, using Gaia distance, we were able to measure the bolometric energy. And also actually using some pan-stars data to perform more detailed spectroscopic, to define more detail the spectroscopic class of the star. Here on the left, you could see different light curves of these flares. So here is the minutes. So these particular flares were found in high cadence pieces of data of ZTF. So you could see that they have a very different morphology. Some of them can be observed simultaneously in two passbands. Some of them are repeating, and this work is actually to show that we have to, and we can, which is more important, to use data from the telescopes, from the surveys that were not specifically developed for this kind of task, to do this kind of task. Because, as I said, for some of the objects, we were even able to measure some astrophysical parameters. So it's possible to do this kind of work with ZTF data. And I would remind you that M-dwarfs are interesting because we consider them as the best candidate to host exoplanets where some life is possible. That's why knowing more about statistics of these objects, their population, and what is more important, about their activity, about these flares, because they have obviously impact on the atmosphere of exoplanets, is a very important task. Among outliers, there are plenty of artifacts, and in in the beginning of our studies, it was really a problem, because if you simply run some isolation forest algorithm, so the first 100 of objects with the highest anomaly scores will be some artifacts. I put some nice examples here, some slew, ghost, this is probably a plane or some track, some diffraction spikes, so many different kind of them. And so the presence of such artifacts in the data really makes life more complicated. And what is also interesting, that sometimes the light curve that produced by these artifacts looks quite okay. For example, here you could see some I-band light curve of a, so each of these points is an artifact, but it could be simply a light curve of some variable star. It doesn't look as a non-real object, but in fact, so this is an object, and this is a fits image cut out, so it's some kind of frame edge and maybe some ghost. So, and each point is like that. So that's why also in SNAD we developed the real bogus classifier, and we use this the results of this real bogus classifier as an additional feature for our active anomaly detection approach. So here you can see how it works. So this is again the fraction of anomalies depending on number of candidates, and without this additional feature, so a lot of objects are artifacts. So a lot of objects among the outliers are artifacts. But if we use the output from our real bogus classifier, so the situation improves, and we really have a little amount of these bogus light curves. So some other things I'd like to share is SNAD ZTF viewer. So if you are working with ZTF data, it probably could be interesting for you. So this viewer was developed by Konstantin Malanchev, so for SNAD, and so it provides you with access to different data releases of ZTF, and so objects light curves in 3 passbands. Also for each point, you have fits image, so you have Aladdin map. You can add the closest span stars object photometry, Gaia object if exist. You can look at the light curves in flux in different magnitude and different flux if you would like to compare with alert photometry. And well, it's not on the screenshot, but there is a cross match with many catalogs and databases, including AFSO VS6 for variable stars, TNS, Simbad, Vizir, general catalog of variable stars, Gaia, well, many different. So very useful tool to work with ZTF light curves. Okay, and yes, here my conclusion. I'm probably a little bit faster. So first, active anomaly detection is a more efficient approach as a standard static anomaly detection algorithm. So working with ZTF data, we created the SNAD supernova catalog. We also created the largest catalog of ZTF flaring stars, so the M dwarf flares. Among the most interesting candidates in anomalies. There are a few superluminous supernovae, including one pair instability supernova candidate, several uncatalogued active galactic nuclear luminous blue variables, cataclysmic variables, and other rare types of variable stars. And anomaly detection system must be built for experts based on its interest and its main domain. Thank you very much for your attention.
Thank you, Maria, for this really nice, interesting talk and for presenting the very useful tool. Thank you so much.